and go back and look at that fourth calculation here. Does this look familiar? Feel familiar? Maybe even feel like something you did in a past life? Set 20, choose 17, stay with me. 0.9 to the 17th, 0.1 to the third, plus 20, choose 18 times something to the 18th times something to the second. Does this feel familiar? It does feel familiar. It feels a lot like expanding binomial, doesn't it? And it should, right? That's why this is called binomial probability, okay? So this should make sense. If you've made that connection in your mind that, hey, this seems like expanding a binomial, then I think that this description will work for us, won't it? In fact, if you expand the entire binomial all the way out and you write down every term of what we had there on the previous one, 20 choose 0, 20 choose 1, all of them, then what would that add up to?
1.
Should add up to 1 if that's all the probabilities, right? Let's see what this says. Binomial probability would be appropriate. The description of this situation would be if we have two outcomes, like the warm-up, heads and tails, right? Two different outcomes. We're going to see other examples today. Engine failure versus success in an engine on a plane. Blackout of pilots at different levels of G-forces. All different things. Do they or do they not fail? In the example we're going to do in a minute, do we pull a widget off the line that's either a functioning one or a defective one, right? And each one of those things is going to be associated with a probability. So if one of the things doesn't happen, then the other does. Probability is P and 1 minus P, right? In here I have them as like success and failure, but obviously like getting a defective widget we're going to consider like a success, I guess. I mean, just for the sake of the problem. That's why there are scare quotes around the success and failure. That doesn't mean like good versus bad. Okay. Then what you said in the warm-up that you observed to be true on the last problem is generally the case, right? We have, if you think like in the warm-up that we had 0.9. Didn't it feel like expanding this in the warm-up? 0.9 plus 0.1 to the 20th. And we had, that's, 0.9 to the 20th plus, and eventually you get to the thing we got, right? 20 choose 17 times 0.9 to the 17, to the third. Was it? Oh, no, it was 17. Sorry. Or 117. 0.1 to the third, 0.9 to the 0, 0.1 to the 20th, plus 20 choose 18 times 0.9 to the 18, 0.1 to the 2, etc., right? That's what that felt like. And like we said, if you expand the whole thing, someone already said it, but why should it be 1? Is it obvious that that all adds up to 1? Why should it be obvious that it adds up to 1 if you look at what we're expanding? Yeah, I mean, this, in fact, yeah, this is not just a fluke here. This will always be 1. P plus Q to the end. I mean, P plus Q is 1, isn't it? So, of course this all adds up to 1. Usually we don't want to add them all up, though. That's not very interesting. What we want to do is add up a portion of these, maybe, like we did in the warm-up, or one of them or something. Anyway, when you're ready, let's actually compute this probability in like manner to how we did on the warm-up. All right, Bruce. You want to talk me through it here? So what's the way to do it? Are you coming up, or you want to? You can come up if you want. You want to write it out? All right. So this is not the whole distribution. Yeah, should it be 0.9? Did you mean 0.992? Is that what you meant? And I think you meant here 150. All right. Yeah, I think we like it now. The only thing I would maybe, I don't know that you need to write this necessarily. This would be the whole distribution. This is all we need here, right? This is all of them. We just want to pick one out. How many terms are in this expansion? Huh? 151, yeah, right? So there are 151 terms in this expansion, 151 probability questions you could ask. We're only asking one of them, right? If you ask them all at the same time, you get the answer 1, though, yeah? Can you have them in view? So I don't know that we need to write that. This equals doesn't feel right to me, right? Is all I'm saying, right? So this is only one of all of them, okay? So did you compute what that is? Someone out there? 0.08? 0.867, can someone confirm? About 8.67% chance of that happening. Is that what we're saying? Okay. All right. If we're going to look at the last problem again here, if we were just to do this like every day, take 150 widgets off the line because we're like all about that quality control. How many do we expect in a given day if we pull 150 off the line? Well, let's say that let's do the coins. If we were to flip coins 100 times and they're weighted so that 90% of the time we get heads, out of 100 times, how many heads do you expect? I think it's pretty clear that the expected value is just the probability times the number of trials you have. Is that pretty clear? Why this makes sense for the expected value of a binomial random variable? So we'll calculate that here in a second for the widgets. It takes a little bit more work to explain why the variance is what I have up here, NPQ, or NP1 times 1 minus P. But both of these are provably true, though. You can start and with a little bit of algebra work, prove both of these results from the definition of the binomial probability distribution that we gave on the last slide. So, but if you take these in faith, then for the last problem, compute what the expected value of our random variable is, our effective number of widgets. is and what the variance is. The expected value will be, how do you calculate it? And what do you get? Maybe you can get that for us. Let me get it. This is still the same example as the last one, right? Right. Alright, so did you get either of these yet? You got the first one? You can just tell me from where you are if you like. Would you just tell me what you wrote? Okay, 1.2. And how'd you get that? And other people got the same thing. And then for the variance, did you do that one too, or?
Yeah, I did that same thing, and then divided by, on top of it, and 2.
Yeah, so just times the last result.
Yeah, I got 1.19.
1.19? Like that? Okay. You guys agree? So what we're saying is, on average, if we do this quality control every day, sorry, NPQ. N times P, I have it, whatever. N is the number of trials, P is the probability. Sorry, I have it backwards up here. Whichever, doesn't matter. That means every day, if we do this in the long run, every day we pull 150 off the line and we check how many are defective. We expect on average to see 1.2 defective ones each day, right? On average, in the long run, if we do this every day. Okay. You gotta have, if you're doing binomial, you gotta have a free throw problem. Now this person, Alex, is like basketball star supreme. It's a little bit high in terms of free throw percentages, but we'll just pretend that he's like a basketball guy. We'll go ahead and do these. I'm gonna call a couple people up to do these. They're just meant to be more like the warm-up today. Just keep practicing here. Get those people are not here. Claire and who? Which one do you want, Claire? Yeah, go for it. Welcome to the stage. Yeah, you got this. And then, what do you want, Cassie? Franklin, can you take C for us? When you ready? No. Please. Yeah, right off the calculation. And you're doing B, Cassie.
Yeah, it's,
Wait, how do I do things? Okay, great. You got it.
No, I don't.
Yeah, you can get it.
Sure.
It's all good. Yeah, that's a good question.
You just do 1 minus. Oh. No, wait, no.
There's a lot of questions and one answers.
Oh, is that what you didn't want to just like, hey, I have a great question?
No.
No, if you speak to me, I was definitely just asking a question. I was like,
That's a great question. Yeah.
Well, I'm asking the
It's a really excellent question. Anyone else want to comment on what a high quality question that was? Okay. So, by the way, if you want a shortcut for doing C, you've already done most of the work, haven't you? By doing A and B, you just
You
need
have
to.
18 and 20.
Yeah, you have 18 and 20. You just need to add 19 in there. And you have them all, right? But yes, stat people will acquiesce here.
That's the point 7. They asked for a faster way to do it, right?
They did. And Franklin delivered. Yeah, so we'll give it away. Thanks, Franklin. It is true that if you want to do B, what's the command there if you want on your calculator? On your calculator, if you go, let's give it all away here. How do you get there, Franklin, on your calculator? How do you get there? Second bars to the distribution menu, and then go down all the way down to binom PDF, or in this case CDF. We'll tell you what those mean in a second here. But for PDF, we're going to enter the same things here. 20, that's the number of trials. You always do the number of trials first. Some of you have fancy calculators that actually say. And then the probability, which is 0.8, and then the value you want. So in this case, 18. And just verify that you also, using that, get 13.7%. Try it. What does binom PDF stand for? What's that short for? Yeah, the binomial probability distribution function. I would probably prefer, I have kind of a beef with the calculator. I would probably prefer that they call that the...
Oh, wait, no, yeah, can you change that for me? It's fine. I didn't do the 1 minus, it was 0.206.
What's wrong?
So I did do the 1 minus, so it was 0.206.
Okay. Yeah, so try this. Should you try it? Everyone push the right buttons. You really are gonna need this for your homework tonight. So go to second bars to the distribution menu and go all the way down to binom PDF and CDF are the two functions we'll need. If you do PDF, you're just asking for, thanks guys. You're just asking for one value in the distribution, okay? And that should give you this. If you do CDF, we need to explain what CDF does. Listen guys, not everyone is taking stop talking. Yeah, C stands for cumulative distribution function. The binomial cumulative distribution function, which a cumulative distribution function always adds up the left tail of the distribution. So unfortunately your calculator isn't set up to calculate it another way. It'll always calculate the probability of, for this, 0, 1, 2, 3, all the way up to the value, and including the value you specified. So do you see why this calculates the exact probability of the things we don't want in this situation? Right? So that's why Franklin says 1 minus this. This is exactly the 0, 1, 2, 3, 4, all the way up to 17, the 18 probabilities we do not want to compute as part of our sum. Okay? So that's the only way to do that quickly. Here it's an option. This was not bad, actually, to do it by hand. On this one, you really have to use the calculator function. Right? We got 300 drivers, and I'm going to ask you this question soon. At least 90 say they text and drive. Right? So what's the probability of that happening? Well, you're going to have to do 90, 91, 92, all the way up to 300. So you kind of need the calculator function here, right?
Do it by hand, guys.
Do it by hand. Yeah, I'll see you in an hour. Right, or you can do the function. So for A, we want what? 300. If we're 300, we're selecting randomly 300 drivers. And 90, we want to ask what's the probability that exactly 90, no more, no less, say they text and drive. By the way, it's important that at all times here that they say they text and drive. It's probably much higher than people actually report, right? But we'll just say that everyone's being honest. Okay. So what's the probability that a given person would be? What does it say? 0.33 to the 90th, 0.66 to the 210. Or you can type in binom PDF 300, comma 0.33, comma 90, and that'll give you your answer. For the second one, again, we want to calculate 390, 0.33 to the 90th, 0.66 to the 210, plus all the way up to 0.33 to the 300, right? And again, this is the right tail of the distribution. We want to do the left tail, so we're going to do Franklin's trick again. 1 minus the sum of the left tail, binom CDF. Well, which are the ones we don't want? 300.33. What goes there? Yeah, up to and including 89, all the way from 0 drivers report that, all the way up to 89 drivers report that, are the ones we do not want to count. Because at least means 90 or anything greater than that, right? So we need to be really careful about this edge case condition. Sometimes you'll have a problem that says more than, or something like that, in which case now you need to interpret the English, right? Your homework is easy. Oh, there is like a couple testing problems. They're not great.
Part of the joke. It's okay, I'm back. Give me a crap.
Okay, guys, see you on Monday.